All right, hey everybody. So my name's Robert. I'm from, I'm from University of Toronto. Today I'm going to talk about applications of monotone constraint satisfaction. So the title of the talk is extremely general. I'm mostly going to be talking about one example today, although there's been tons of kind of work in this area. So it's kind of an exciting place to stay. So to sort of get in line with our concrete example, let's start with a stupid question, which is how hard is it to prove stuff, which I'm sure that all of us are intimately familiar with. So I mean, like, to formalize this question is really like just the purview of propositional proof complexity, which is like literally the study of how hard it is to prove stuff, right? So what do I mean by stuff? Well, I literally mean, tautologies, right? So there you go, tautologies over some propositional set of variables. So we're not going to be talking about like super complicated areas where we don't care about quantifiers and things like that. We're just going to be dealing with propositional variables. So another dumb question is, what do I mean by prove? And so prove just means to prove. We're going to fix some proof system in the background, some system of just deduction rules, a way to take two formulas and produce a new formula that follows from it. And by hard, I just mean how long are the proofs going to be, right? So ideally, we would like to be working in some sort of proof system which is strong enough to produce short proofs of almost everything, right? OK. Well, so here's the sort of the formal version of the question that we're going to talk about. So we fix a proof system P, and we're going to fix a tautology. And we just want to ask how long should proofs be, right? OK. Well, I mean, this kind of suggests the next natural question, which is, what does a good proof system look like, right? And I kind of alluded to it a second ago, but I mean, really, there's two essential properties and one nice property that we would love to happen. So the two essential properties would be, first of all, that every tautology has a proof, right? Everything needs to have a proof, or else it's just dumb. If I have a proof system that only proves one thing, then it's not really doing anything for me. The proofs should be efficiently verifiable. If I have a proof system and I bring to you, and I say, hey, I got a proof for you, and I bring it to you, and then you can't understand it, or you can't verify that the individual steps are sound, then it's useless. So these are the two essential properties that any proof system should have. And the final property, which would just be a nice property to have, would be that all the proofs are short. You know what I mean? And by short, I mean in terms of the length. If the length of the input tautology is small, then the length of the proof should be like polynomially bounded.
Maybe you should add if you want to prove sound.
Oh, soundness is good too. Yeah. Well, well, OK. I mean, yeah. Oh, yeah, sure. Yeah. Maybe we should add soundness too, just in case we don't want to prove everything.
I guess that comes in with efficiently verifiable.
Well, no, not necessarily, because a proof system can be efficiently verifiable in that if I look at a single step of the proof, I can easily tell whether or not this step followed from the previous steps. But it might be really long. Each individual step could be easy to verify, but the proof could be very, very long. So the whole proof wouldn't be efficiently verifiable.
Let's see. I think you're soundness.
Yeah.
Follows if verifiable is what we think.
Yeah, that's true too. OK, so kind of the landmark result in this kind of area is that a proof system satisfying these three properties is going to exist if and only if NP equals co-NP, right? And this is closely related to problems in complexity theory, because if NP is not equal to co-NP, then P is not equal to NP. So Steve Cook and his student Reckhow at the time sort of were interested in studying these sort of things, and then they sort of realized this connection between NP and co-NP, and now from this we kind of get a natural program to attack NP versus co-NP, or P not equal NP if it turned out to be different. And that's just, start with weak proof systems, things that are really, really weak that we can understand really well, prove lower bounds against them for certain tautologies, and then over time, make the proof system stronger and stronger and stronger. And then maybe we can improve our lower bound techniques to make them stronger and stronger and stronger. And then finally, we can engage with NP versus co-NP in kind of full generality. Right? OK, so it's been, I think it's been remarkably successful. So here's like just a fragment of some of the proof systems that have been studied.
Polynomially bounded, you mean in the length of the...
Length of the tautology, yeah. So it's been kind of like remarkably successful. I mean, this is just like sort of a fragment of the proof systems that have been studied. Sort of these Boolean proof systems over here are probably what you would think of initially if you thought of a proof system, like the lines are some sort of Boolean tautologies like formulas or something, and we have the sort of natural deduction rules on them. But we also have sort of more exotic examples of proof systems. So over here on algebraic proof systems, if you're familiar with like the Nullstellan sets or things like that, you can view algebraic theorems like that, connecting algebraic geometry to commutative algebra as funny, as proof systems in their own right. And also in the center, we have these semi-algebraic proof systems. And by that, I just mean sort of proof systems which deal with inequalities over like the real numbers of the complex, or over the real numbers, right? So these typically have like a geometric kind of flavor. And they also have sort of close connections to optimization and inapproximability. So in terms of our ability to like engage with proof systems, we're also doing quite well. So below the line kind of represents proof systems that we can actually prove lower bounds for. Yeah, like we've been sort of remarkably successful, although the next step on this slide, at least across this line, has sort of been a very long-standing open problem for many years. So, there's still lots of work to be done to sort of explain what's going on down here.
What's IPS?
IPS is the ideal proof system, which is this proof system introduced by Tony and Josh Grochow. Yeah. It's very recent, like 2012 or so. Yeah. So how do we actually like sort of engage these proof systems? Like how do we actually prove like lower bounds against them? Well, this might be controversial, but I'm going to claim that broadly speaking, there's roughly like 3 techniques. And they're not mutually exclusive. They overlap in all sorts of ways. And so the first way, this might be the most controversial of all of them, is just more or less ad hoc arguments. You like look at the proof system, you think really hard about it, maybe for like a week, maybe for like a year, and then you come up with some way of figuring out how to prove like a lower bound for it, right? Like we kind of directly engage the proof system on its own terms. There's sort of a more general technique called interpolation, feasible interpolation. And this allows, in some cases, sort of a limited reduction to circuit complexity lower bounds, right? So it's kind of strange to reduce, a field that we don't understand that well to another field that we don't understand that well. But it turns out that this is actually, like, with the circuit lower bounds that we do understand, this can be applied to sort of get great results. And finally, when both of these things fail, usually the only real techniques that remain are sort of not quite reductions to circuit complexity, but using circuit complexity inspired arguments. So if you're familiar with like the switching lemma, this has been kind of directly used to prove lower bounds for proofs where the lines are like low depth circuits. Okay. So just to refer back, I mean, roughly speaking, what do these systems look like in relation to what kind of lower bound proofs that we have that can engage with them? I mean, below the red line is where we more or less have any lower bounds at all. Below the blue line is where we can get interpolation to work. And below the green line is where we kind of have these nice, more of a like direct understanding of how the proof system behaves, right? So there's 2 obvious outliers, right? So the first is AC0 Frege. And that's the proof system I was talking about a second ago, where the lines of the proof you should think of as being like formulas of a restricted nature. And it turns out that interpolation is actually it cannot apply, right? It actually does sit in this space where we have any lower bounds, but it does not have interpolation under a reasonable cryptographic assumption. And then the other obvious problem here is cutting planes. And cutting planes is an interesting case because we still don't know how to engage with it sort of directly, but we can get lower bounds out of this interpolation argument. So what's interesting is actually we more or less can only use interpolation. It's the only technique that we have for engaging cutting planes at this point. And now this would be fine if interpolation was kind of fully general. If I could say start with any formula and use interpolation to just reduce it to a circuit lower bound. And I know that that would be like equivalent, right? Like some sort of equivalence there. But this turns out to not be true. So let me talk about interpolation just in a little bit more depth. So interpolation, roughly speaking, we're interested in proving propositional tautologies, or equivalently refuting unsatisfiable tautologies just by negating them, right? And so with interpolation, we're going to start with a formula which looks to be, which is sort of in a very specific form. Okay? So in particular, it's going to be split into two pieces. So it's going to be on three sets of variables, x, y, and z. And now these z variables are going to be shared between 0 and the 0 formula and the 1 formula here. But the x's and the y's, they kind of don't interact initially. So associated with this formula then, if it's actually unsatisfiable, if every assignment falsifies it, is sort of this natural Boolean function, right? I plug in a value for the z variables to the formula, and I check which side is unsatisfiable. If f0 is unsatisfiable under this assignment to the z's, I output 0. And if f1 is unsatisfiable under this assignment to the z's, I output 1. Right? And this is just, this is interpolation in a nutshell. It connects proving this thing is unsatisfiable to computing this Boolean function. Okay? So more formally, I mean, we start with a p proof of f in some proof system p. And we can somehow translate this proof directly into like a circuit or an algorithm which computes this Boolean function, such that these things are of comparable size. And this allows us to sort of translate circuit lower bounds down here back into proof size lower bounds up here. Yep?
Let's see, I guess, is there an issue if they're both unsatisfiable?
No, we just output 0. Yeah.
Well, I mean, it's more generally you can just request that it's output 0 when f0, you know, when only one of them is true, you answer that one, and when both you can answer whatever.
Yeah. So this is kind of, there's a long history of sort of studying this thing. It sort of starts with the Craig interpolation theorem all the way back in 1957, which gives interpolation for just regular Boolean formulas. But feasible interpolation of this style, where we actually take a proof and we turn it into a circuit of a comparable size, this started being studied sort of heavily in the 90s and in the late 80s. And there's been sort of a long line of works translating these things and proving circuit lower bounds to get lower bounds on the proof systems. And it's very general when you can apply it, but the obvious problem is that it only applies to these split formulas, right? Like, this is not a fully general way to write down like something that we'd like to prove, right? Like, not everything we want to prove looks like this. You know, things we want to prove look obviously more general than that, right? And so this is why cutting planes is in kind of this unfortunate situation where it has feasible interpolation in that we have some circuit complexity, problem that we can reduce it to, but we don't know how to engage with it. Like, we can't directly prove lower bounds. So the only lower bounds for cutting planes are for formulas of this form. Right? So I guess the main concrete result I'm going to talk about today is sort of the first step past this line. Okay? So just to kind of remind everybody so that we're on the same page, we're going to be considering sort of random SAT instances. Okay? So basically, I fix some width k. I'm going to choose clauses of width k over some fixed set of n variables. And I'll choose m of them with replacement, okay, uniformly at random. So it's known that, the clause density, like this, like taking m and dividing it by n, this kind of controls how hard this formula is. Like, if I take m, if there's lots of clauses, then it's going to be unsatisfiable with very high probability. So I can talk about proofs of it. And there's kind of all this famous work about, what happens near the threshold. Like, that's where things tend to get interesting, where we're not sure if it's unsatisfiable or satisfiable. And so today we're going to talk about how to prove that these random SAT instances actually require exponential size cutting planes refutations. So this was proven independently by Pavel Hrubesch and Pavel Pudlak. And it's the first lower bound for cutting planes refutations of a formula split. Split in the sense that I drew on the last slide. We have these variables partitioned into two subformulas. Okay. So how do we prove such a thing? Like, what's kind of the main step of getting past this? Well, it's actually going to be calling it a generalization of an interpolation is almost right, but it's not exactly right. What we're going to do is we're going to show that a proof system which is related to cutting planes, which can simulate cutting planes, which we're going to call RCC, is actually equivalent to real monotone circuits, computing a related Boolean function, which I haven't talked about yet. Right.
Is a line in the cutting plane refutation just a cutting plane?
Yeah, it's like a linear inequality. Yeah, and then given For the purposes of this, you can just imagine that we have two lines like that, and we can just deduce any line that follows from it. The lower bounds apply even to that stronger system. So we're going to show that these RCC refutations of f are actually equivalent to computing some related function. But this is not the interpolating function, because there is no interpolating function, right? It's just some unsatisfiable CNF. I can't, since it's not split, I can't associate like this natural Boolean function anymore. I've got to come up with some other Boolean function. And I'm going to show that computing this other Boolean function is actually equivalent to the proof side, to refuting this. And then so from this, we can just prove lower bounds against the monotone circuits. And real monotone circuits are extremely well understood. Like, we're very, very good at proving lower bounds against them now. Okay. So what do I actually mean now about this function here? Well, I'll talk about it in a second. So you can just think of it as like lines where, yeah, okay, cool. So yeah, and to get this equivalence, we're going to modify sort of these recently developed tools in communication complexity, which are this is the monotone constraint satisfaction problem, which I alluded to at the beginning of the talk. Okay, so let's take a peek in the toolbox, just in case. But if there's any questions now, it'd be a good time about kind of the general setup. Okay, cool. So what's an RCC proof? Okay, well, I'm going to simplify things for now, and I'm going to kind of ignore the real like cutting planes for a second, and I'm just going to talk about communication complexity proofs. So the idea is that we start with an unsatisfiable CNF where the variables have been partitioned into two sets, x and y. Okay, and if you like, you can start with any unsatisfiable formula and just partition the variables in some way. It doesn't matter. Okay, and now a communication proof is just going to look exactly like you'd expect. It's a proof. So the first lines of the proof are the clauses, and the later lines are just other lines which are deduced from earlier lines. Okay. Since this is unsatisfiable, the last line is going to be identically 0. So we can deduce the identically 0 function. And we're going to put a constraint on these lines in that each line can be computed by a low-depth communication protocol. Okay. So this is the main the main constraint on this thing. Each of these functions, with respect to this variable partition, they're deduced from earlier lines, and also they have a low-depth communication protocol. Okay? And I'm dealing with full semantic inference. Like, I'm not putting any constraint syntactically on how we can deduce lines from each other. So in particular, these are not efficiently verifiable proofs. Our lower bounds are actually stronger than that. Okay. And I'm going to let CC proof be the size of the smallest CC proof of f. And now to answer your question about what is an RCC proof, well, now it's going to be the same setup, except the communication model now is the real communication model, where Alice and Bob hold inputs, and they exchange real numbers with a referee, and there's sort of a natural model that's related to that.
Is it related to this computing an expectation?
No, it's a bit different. Yeah. Okay. So I'm going to state sort of this. Just to kind of stay in a realm where people are probably more familiar, I'm going to talk about sort of communication protocols now. I'm not going to talk about this sort of different real communication model, although you can imagine all these results just lift to this real communication model, which I haven't mentioned in a pretty straightforward way. And now sort of the main step of this translation proof is we're going to prove that these CC proofs of f, if I start with f, which is unsatisfiable, and I take any partition of the variables, then I can construct this sum monotone function such that CC proof size is exactly monotone circuit size. Okay? And the reason I'm putting this sort of a prox here is because, remember, I didn't really specify CC directly. I just said low-depth communication protocol. So if low depth means constant, then this is actually like a big theta. Like this is like tight.
Actually, I have a question about the previous.
Yep.
So it sounded like, okay, so the first thing was some kind of semantic reduction.
Yep.
Okay, I think I see. And the other thing is just about each function should be a simple function.
Yeah.
And I guess the reason why you can't just you can't choose fi to be 0. I mean, 0 itself is a simple function, but it doesn't follow from just two clauses.
Exactly. Yeah.
It has to follow from two creators.
Yeah. Exactly.
In a resolution, you have the axioms are contradictory, but you cannot manipulate immediately.
Yeah. So because it's semantic inferences, like arbitrary semantic inferences, if for some reason I could like use all of these in one semantic inference, I could be finished in one step. So there's like a locality thing going on wherein I can only look at 2 things at a time. Yeah, does that make sense? Cool. OK, yeah. So this is kind of the main translation theorem, which I'm going to hope to try and communicate. So yeah, so the CC proof size of f, there is a partition of, like under any partition of the variables with respect to which I do these communication protocols, I can translate into a function where the circuit size is approximately the same. Okay. And so how do we do that?
Sorry, monotone means
no
negation?
Monotone means no negation in the circuits. Yeah, a monotone function is like a monotone function in the normal sense. X less than y is fx less than fy. Yeah. So let me now actually define this CSP function. Okay. So I'll define it generally, and then I'll talk in a little bit how we can sort of relate these two. So if you're familiar with sort of constraint satisfaction, this is kind of the natural way to turn the constraint satisfaction problem into a monotone function. And by a monotone function, I just mean, the input is a string of bits, and if I flip any bit from 0 to 1, I can't flip the output from 1 to 0. Right? So we're going to have some fixed constraint graph, right? So in the normal CSP, these constraints are sort of fixed from some constant number of templates or something, and this constraint graph is allowed to vary over its inputs. But we're going to change it a little bit. We're going to fix the template h, so the constraint graph is going to be fixed, and then the input is going to be the truth tables. So we're going to describe as input what the constraints actually are in the most generic possible way. So I'm actually going to write down for every single constraint here the truth table of the satisfying assignments to that constraint. And for the sake of simplicity, we'll assume these are all Boolean variables. Okay? It's 2 to the d, to the degree. Yeah, that's very important. Yeah, exactly. So this is only going to work for constant degree constraint graphs, right? Because if the constraint is too big, then my input's going to be exponentially long. So I'm going to assume that these are always d or maybe log n. Log n's OK too. Yeah. And now the output is just the normal output of the constraint satisfaction problem, right? We just decide if there's a satisfying assignment which satisfies all the truth table inputs. Right? So now this is clearly monotone, because if I take any of these truth table bits and I flip it from a 0 to a 1, I'm only making the CSP easier to satisfy. Right? Any satisfying assignment that existed before will still exist after. So, yeah. So I claim that this is a very natural way to turn CSP into a monotone function. Okay. So now, how do we translate these proofs into computing this thing? Okay. Well, the main thing is, as an intermediate, we're going to use communication complexity. So we're going to start with this function f. And we're going to take just an arbitrary partition of the variables. Okay? So this is going to partition the variables in every clause. Now, some of these clauses could depend only on x or only on y. That's perfectly fine. Okay? I'm just drawing it like that in full generality. So what I'm going to do is I'm going to relate these CC proofs to this search problem. Okay? So associated with this unsatisfiable CNF is kind of this natural communication task between 2 players. And it's just the following. Alice gets some input x, and Bob gets some input y. And then they want to just output one of the clauses that's falsified. Like output the name of a clause that's falsified by that assignment.
That's the usual communication tasks that appear in previous in reductions, in interpolation, or in other.
Yeah, absolutely.
Such problems related to proof systems.
Yeah, absolutely. Yeah. So the one thing that's a little bit different is that, well, maybe not that different. I mean, if you dig deep, it's still been observed. But is that we're not going to be considering normal communication complexity here in terms of like the depth of the protocol. We're actually going to be considering like a DAG-like protocol. And the best analogy that I can give here is kind of considering like circuits versus formulas, right? So just like a circuit is like a formula where I've like recursively collected all the repeating subcomputations. In this communication protocol, in a communication protocol, which is normally like a tree, I can think of as a tree, I can take the identical thing, like the subcomputations which are identical, and kind of collapse them together. And then I'm going to actually measure the size of this. And now we didn't prove this, just like Avi mentioned, that this connection has been known for quite some time. Okay. So on the other hand, for the computation task, I mean, there's sort of a standard way to.
So maybe you want to define. It's not labeled by either Alice or Bob.
Yeah.
And what they transmit on this wire is a function of their.
Yeah, that's right. Yeah, that's one way you could do it. Yeah, so it's basically so it's a branching program. Yeah, exactly. So yeah, it's a branching program. At each node, there's a communication happening, and then they choose one of the nodes to go to based on what they evaluate at that place. Yeah. So on the bottom, there's kind of the natural. There's the very well-known connection between circuit size with the CSP and sort of the Karchmer-Wigderson game, right? And this Karchmer-Wigderson game holds for size. This was shown by Razborov back in the 90s. And then this main step in the middle is kind of the place where this CSP function works. So it's where we can actually show that this search problem and the Karchmer-Wigderson game are going to be the same. Okay? So most of the work in the reduction is going to go in here. And this is also like a known reduction. So more or less what we're doing is we're just stringing together results that have been known, but in a way that kind of people didn't observe before for proof systems. And it's even rough to say that people didn't observe them before, because I think all the ideas were just floating there up in the air. We just kind of picked them out and strung them together, right? Perhaps the biggest thing that was missing at the time was this connection between the search problem and the CSP. OK, so let's try and talk a little bit about each step of this reduction. OK, so first I'm going to talk about how we relate the proofs to the search problems. Like Avi said, this has been kind of long known. There's a pretty straightforward way to translate a proof, one of these CC proofs, into a protocol. OK, so suppose we have some unsatisfiable thing, and I've partitioned the variable somehow, and I have some proof of it in this CC model. So at the leaves, we have these clauses. For each pair of guys, I'm doing some semantic inference into a function that has low communication complexity. And then eventually I deduce 0. Okay? And I want to translate this into a protocol for the search problem. So given some input x and y, find a clause that's falsified. So all we're going to do is we're just going to use the fact that the proof is sound. Right? So if I just start by looking, say, at the last step, well, from this step, I know that fs and fs minus 1 logically imply 0. So what does that tell me about x and y? Well, it tells me that for every input to the x's and y's, one of those things has to be 0. Right? Just by soundness. And so this means that Alice and Bob can just evaluate both of them, see which one is 0, and recurse there. So if they start here, they evaluate both of their functions. These are both low-depth communication protocols, so they can do that efficiently. So maybe they find out that fs minus 1 is 1 on their input, but this one's 0, so they go there, right? Then they look at their inputs there, and they recurse, and then they can, in this way, they can walk down the proof all the way to a clause, and then they just output that name, like that name. Does that make sense?
So this is exactly the same thing that Beam, Pitassi, and
yeah, exactly the same.
Did, only that they didn't look at the size of the tree. They looked at the size of the branch program. They looked at
It's exactly right. Yeah, yeah. Just like Avi pointed out, this is just exactly what this paper back in the 90s did by Beam, Pitassi, and Raz, where they did the exact same thing. They just weren't tracking the size of the proof. The real observation here is just that here we have this DAG-like proof, right? The proof is in general a DAG, and this communication protocol, it has a lot of redundancy in some sense. Like at a lot of places, I'm going to be doing the same thing once I hit a node. So I can just fix these sizes to be the same. OK? Cool. So that step's done. So for these two, I'm going to switch to the last one. And I'm just going to do a quick review of the Karchmer-Wigderson game. I expect a lot of people here are familiar with this. So the input is just some partial function. OK? And then we have two players, these Alice and Bob. So Alice gets a 1 of the function, and Bob gets a 0. And all they want to do is they want to communicate bits back and forth and then output some input index that's different on Alice's input versus Bob's input. And we know that an index has to exist because Alice gets a 1 and Bob gets a 0, right? So it's kind of very well known right now, sort of proved by Karchmer-Wigderson back in '88, that the communication complexity of this function, how many bits have to be exchanged for this protocol, captures exactly the circuit depth of the function. And like I mentioned earlier, Razborov proved in 99 or in 95 that actually if you consider the size of a DAG-like protocol, then this is actually the circuit size of f. Okay? And moreover, all of this holds for monotone functions in sort of a stronger way. So let's suppose now that this input function is monotone. So remember, so a function's monotone if the input increases, then the output increases. And I'm going to, since this is a partial function, I'll just say it's extended. It can be extended to some monotone function. Okay? So if we know this about the function, I can strengthen this output guarantee, right? Instead, I'm going to enforce that they actually have to output an index where Alice has a 1 and Bob has a 0. And one of those inputs has to exist because the function is monotone. And now we can say something stronger about the results on the bottom. In fact, the communication complexity of this game where I've got to actually output this index where it's 1 and 0, well, this actually captures monotone circuit depth and size. And this is nice because monotone circuits are something we can engage with. And in this case, we can use circuit lower bounds to prove lower bounds of the communication complexity. And here, we typically use the communication complexity to prove lower bounds on the circuit depth. Okay?
So this means that for those problems, the monotone circuits and general circuits are the same?
No. Okay, so that's a thing. So this is a stronger task. This is harder to do. So this makes it easier to prove the lower bound, right? So for instance, in this case, Alice could have a place where it is 0 and that's 1, right? Yeah.
But in general, it's not only the depth or the size. You have exact
Yeah.
same thing, right? So the protocol is
The same object.
Yeah, it's the same object. Yeah, exactly.
Only
Yeah.
one goes, the computation goes top down and the other is bottom up.
Precisely. Yeah.
David, one way to always convince us that this is a much harder task than the task in which they just have to output an index where the values are different is that the second one always has a randomized protocol of log n bits. That's basically hash.
If
you and I
say
just
want to
have
output
to-
a different bit.
Yeah. If you and I just have to find a bit where we differ on different inputs, we just ask, you would find it. But we
So,
cannot. There is no way to guarantee that I will have a 1 there and you will have a 0 there.
I see. So for monotone circuit, it's not true that you can always do.
Not only it's not true, many low bounds extend to the randomized model. So even probabilistically, you cannot do it faster than linear or something.
Cool. Yeah, OK. So this step is also done. Now let's talk about this sort of central step here, where I'm going to relate the search problem and the Karchmer-Wigderson game for this new function. So I'm going to start. So I want to relate these two things. And I've got this unsatisfiable thing. Okay, and I've partitioned the variable somehow. And I want to somehow translate it into an instance of this funny CSP problem. So the idea is to just take f and use the topology that kind of already exists as my constraint topology. So, so for instance, I'm going to just project onto the x variables.
Well, what do you mean topology?
I just mean how the variables are connected to the clauses over here. So if x1 occurs in clause c1, I'm going to add that edge. Okay, so it's just the constraint topology. I'll call that the constraint topology of this CNF.
So
Okay.
what otherwise?
So right. So this is the funny thing about this reduction. So I'm only going to project on the x variables, and I'm going to use the x variables to produce ones, to produce truth tables which are ones, and the y's which don't occur are going to play an important role in producing the zeros of the function.
You're going to create one of these interpolation problems.
Yeah, more or less. In some sense. It's
Is it good to think about it this way or not?
yeah. I think so. I think so.
You're creating somehow an interpolation instance for an arbitrary instance.
It's not really quite like that because, I mean, the difference between at least the way that I think about it, the difference between interpolation and this is that with interpolation, you want to find it. With interpolation, you have this very specific function where one of these things is going to be falsified, like it's like a Boolean thing. Whereas here, we're really solving the search problem. Like it's like a multi-output thing. So it's not quite right to, I'm not sure. It might be helpful to think about it as interpolation in some sense, but this is kind of a crucial difference.
In almost all the multi-output Bas-Pudler games, I mean, the usual search problems for unsatisfiable CNF, where you want to output the name of a clause which is violated by the input. It will still be hard to just give a bit about whether it's it's in the left side of the clauses or on the right side of the clause.
Yeah, that's true.
That's almost always the case. And is this closer to?
That's closer. Yeah, that's closer. Yeah, that's actually closer. But I think that's closer, and maybe you'll see it when I actually write down the reduction. So, so focusing on the x variables. So the thing is, we want to reduce this search problem to this Karchmer-Wigderson game. Okay, so we're going to take x's and y's, and we're going to design truth table inputs using v's, such that the search problem in this game are essentially equivalent on these inputs. Okay, so it's just a reduction. And so how do we actually do that? Well, let's actually write down what the truth tables look like. Okay, so I'm just taking, for each of these constraints right here, I'm just going to visualize the inputs as like truth tables like this. So each table only depends on the variables. Yep.
So you're just taking this formula and now you are creating a CSP.
Yeah, exactly.
So only on the CSP, the constraints will have the same names.
Mm-hmm.
I mean, they are not the same clauses. They are just constraints. They happen to be the same names.
Exactly.
And there will be constraints on the x variables.
Exactly. Yeah. It's like I've taken the CNF, I've thrown out the y variables, and I've forgotten that these are clauses. And I'm going to come up with some other ways of defining the constraints. Okay. So these variables are going to be just the x variables of the clauses, because that's the input to the truth table. Okay. So we start with, so how do I take Alice's input and I want to map it to a 1 of the function? Like a truth table that's a CSP instance that's satisfiable. Okay. Well, it's actually quite simple. So since the CSP only depends on the x variables, right? I can just take her input, and for every single clause, I'm just going to project her input onto those variables, right? And then I'll just fix those to be all 1s in the truth tables, and I'll set everything else to be 0.
Red is 1.
Red is 0, green is 1. So this is going to be satisfiable because in this CSP instance, the only satisfying assignment is x. Yeah, it's like I'm planting a unique satisfying assignment. It's like I have this constraint. I've forgotten that they're clauses, and I get to define the constraints however I want. So I'm going to plant a unique satisfying assignment, and that's just going to be x. And it'll be unique under the assumption that all these guys actually contain x variables.
Yeah, so the y's can still satisfy these clauses in a different way, but that will, no matter what y is, this x will satisfy that.
Exactly. Yeah. So this instance is clearly sort of satisfiable. So it's definitely a 1 of the function just by plugging in x into the constraints. And now for the y's, what we're going to do is we need to map this to a 0 of the function. And now we're going to use the fact that this thing is unsatisfiable. Okay? So this is a bit weirder. So what I'm going to do is for each truth table, we're going to look at like each of these lines of the truth table corresponds to an assignment to the x variables, right? So what I'm going to do is I'm going to take that assignment, say like alpha, and I'm going to take that assignment and y, and I'm going to plug it into the clause, and I'll just write down 0 if it happens to be 0. I'll just write down whatever the clause outputs on that assignment. So since every clause has a unique falsifying assignment, with just one assignment to the x variables and one assignment to the y variables, each of these truth tables is going to have at most 1 0. Right?
What does the width of this truth table represent? Just, I mean, each box only contains
2 to the d assignments.
Yeah, no, but it's just it's just 0 or 1.
Yeah, just 0 or 1. Yeah.
Can you repeat why we have one?
So because, okay, so for every single assignment alpha in the truth table, if I take the truth table C1, say, and I look at alpha, I'm just going to plug alpha into the clause. This is where I'm kind of mixing notation a bit. Here I mean, the index of the clause. Here I mean the actual clause from the underlying CSP. Okay? I'm just going to plug in alpha and y and just see what value that is, and then write that down in that entry for the truth table. So since it's a clause, every assignment except for one is going to satisfy it, right?
It's a CNF clause.
It's a CNF clause, yeah. So it's just a disjunction of literals. Yeah, sorry. Okay, yeah. Yeah, it's a disjunction of literals.
Misleading. I mean, not misleading. I mean, I guess to get used to your notation. I mean, in what you write is a truth table. It's really all the 2 to the D binary patterns for the D variables in every clause or whatever it is. And the colors tell you the function value.
Yeah, exactly.
Green is 1 and red is 0.
Yeah, exactly.
That's the way you present the truth table.
Yeah.
So, yeah, I'm confused about something. I'm confused about the previous slide.
Yeah.
In that, so it seems like there you have a particular x.
Mhm.
Aren't we in some sense searching over all x's?
Yeah, so this is like in some sense I'm reducing a communication problem to another communication problem, right? So I want to reduce this search problem to the Karchmer-Wigderson game for this guy, right? So if I can solve the Karchmer-Wigderson game, I should be able to solve this problem. So Alice and Bob get their inputs. So Alice gets an x and Bob gets a y. They privately map their inputs to inputs of the Karchmer-Wigderson game, and then they run the protocol for the Karchmer-Wigderson game. So that's why I'm only going to consider how to map one x at a time, right?
The x that that player gets?
Exactly. Or the y that the other player gets. Does that make sense?
I have to think about it a bit more, but yeah.
Yeah, now why not? Why not take it now? So
Yeah.
it's a reduction between two communication games. In both cases, there is Alice and Bob. The first problem is this communication problem, right? That's coming out of the falsifying, this search problem of finding out which clause is violated in this unsatisfied CNF. And now each of them, privately transform their input. One will be a satisfying assignment for the new CSP, right? This was how the X is translated to a truth table, right? To a truth table which will be satisfied by the CSP. And so that was this slide.
And only for that x.
Yeah. So for this one x, I'm going to map it.
This X will be translated in this translation. So the input to Alice, which I guess holds X, is a truth table that satisfies the constraint abstraction.
It's translated into this
list of truth tables.
These list of truth tables, which are only satisfied by that x.
For which X satisfies the CSP. The CSP is given, the sort of the structure of the CSP is given, the connection of the constraints to the variables F. So this seems to satisfy it. And now similarly want Bob to have truth tables for which falsify the CSP.
Right. Does that make sense? This is kind of the most non-trivial part of this reduction, for sure, by quite a wide margin.
Last question.
The
Yeah.
communication game for the CSP thing is that both Alice and Bob, Alice gets a satisfiable CSP instance,
Yeah.
Bob gets an unsatisfiable one.
Yeah.
And they want to
Find a truth table entry where Alice has a 1 and Bob has a 0.
Okay.
Yeah. And so green means 1 and red means 0. Just okay, cool.
Well, the input's not satisfied.
Sorry? Yeah, good. Great question. Yeah. So hopefully for this 0 instance, which is a little bit funny, we're just going to take the clause and just plug in the value of the clause when I evaluate it, right? So every assignment to the x variables except for 1 is going to satisfy the clause already, right? So that's why these truth tables are going to look entirely green except for maybe at one spot where all the x variables are the right values to falsify the x part of the clause, right? But then, depending on what y has, I could either satisfy or falsify it, right? Like sometimes y is going to satisfy the rest of the clause, and then the truth table will just be entirely green. But other times, y with this alpha is actually going to falsify the entire clause. And then, because I'm just writing down whatever the output is, that's where it'll be 0. So every truth table is going to have at most 1 0 in it. Why is this a 0 of the function, which is not the easiest thing to see like right away? It's just that suppose that it wasn't a 0 of the function, okay? And suppose I had a satisfying assignment for this. Well, then that means that there exists an assignment to the x variables such that all the truth table guys are going to be set to 1 there. But if that was true, then by the definition here, I would have satisfied the formula. Right? But that's impossible because the formula is unsatisfiable. This is like the main trick. This is why the y variables don't occur, kind of. They're being used to generate the zeros, but they don't occur in the actual CSP itself. Does that make sense?
I mean, I think the y variables allow you to specify different instances of the CSP.
Yeah. But they'll all be unsatisfiable when I generate them this way. Yeah. Just by the unsatisfiability of the CNF. Okay?
Is the reduction work just because it's a clause, or will it work for any?
It'll work for anything. Yeah. In general, we don't actually split the variables up like this. Usually in like the communication complexity setting, we start with f, and instead of splitting up the variables like this, we plug in like a gadget, like a little function that like takes in 2 inputs and like outputs a bit. And then the exact same reduction works wherein you just replace all these guys with the inputs to the gadget instead. This might be the more familiar setting if you've ever read any of those kinds of things. This is actually like kind of the simplest way to do this in some sense. I'm just going to partition the variables arbitrarily, but it works in a much more general setting. Yeah. And it doesn't even have to be a CNF. It can be an arbitrary search problem as long as it's total, as long as there's always an output for any pair of inputs, right? Because all I have to do, if this is an arbitrary search problem, I'm just going to plug in, whether or not the search problem is satisfied on these 2 inputs. Cool. OK. So why does this reduction actually work? Okay. Why does it actually reduce the search problem of finding an unsatisfied clause to finding a 1 and a 0? Let's just look at a clause. Okay. Let's just pick out one of these truth tables. Well, on the 1, remember that let's suppose that x and y actually falsify the first clause. Okay. Well, then by the way that I've defined the x's, there's just going to be 1, 1, and that corresponds to the restriction of x at that area, right? And then on the zeros, this is going to be the one place where the clause is falsified, right? Because since x falsifies the clause, it's all of its variables. And similarly, y must have falsified all of its variables. So when I evaluate this clause on x and y, it must be 0. So on Bob's input, this truth table bit is going to receive a 0. So that right there, this is an answer to the Karchmer-Wigderson game, right? And in general, whenever you have a solution to the Karchmer,
you are supposed to return an index.
Yeah, so I'm going to return this index right here, this index of this truth table. So on this index, it's 1 on the 1 and 0 on the 0, so it satisfies the requirement. And by the way that I've constructed the problem, this is only going to be possible if that clause is falsified. So in general, any place where this is like separated like this, it can only happen if the underlying clause is actually falsified, right? Because this is almost entirely due to the y's, because I've plugged in for the y variables what this clause, like the output of the clause on the x's and y's. Does that make sense? Yeah. This is an extremely clever reduction. It was introduced by Ross and McKenzie back in '97, and it's actually introduced kind of implicitly. They introduced these sort of Dart games, and then it wasn't really realized. It's quite likely that they maybe understood it in this sense, but they definitely didn't write it down that way. And it was, like I said, introduced to separate the monotone NC hierarchy, so to separate different levels of circuit depth. Okay.
Why don't you go run states again? Why? In fact, we want to say that every clause that is false can be output by this. This is exactly the set of potential outputs for the players.
Oh yeah, sure.
On X and Y.
Yeah, sure. So on the 0 inputs here, right? On the 0 inputs, I'm just going to be writing into the clause, into this area in the truth table, exactly the value of the clause of that thing.
I see. So
So-
Bob can only agree to output it only if it has a 0.
Exactly, yeah. So
So it has to be false.
if a clause is falsified, Bob's going to have a 0 there. Those are the only places where Bob's going to have a 0. So all the possible outputs are like that.
So 1 for Alice means that alpha equals X.
Exactly. On those variables, yeah. So all the outputs are going to be exactly the clauses which are falsified. So this is why this is like really like an equivalence, right? Like I can actually go back too. If I can solve the Karchmer-Wigderson game here, I can easily produce instances here just by picking out the where the clause is falsified. So is everyone clear on this before I continue? Cool. Yeah. Yeah. So like I was saying, it's a really clever reduction. It was introduced by Ross and McKenzie. It's closely related to these lifting theorems and communication complexity, where normally they don't partition the variables. They introduce these sort of 2-player gadgets, and then that allows them to reduce like communication problems to solving query problems, like decision tree complexity. And it's been used for a lot of things, and this is kind of the applications of the monotone constraint satisfaction, because this is just yet another one in some sense. So it's been used to obtain extremely strong circuit complexity lower bounds. So Ross McKenzie separated the monotone NC hierarchy. The strongest circuit complexity, the monotone circuit complexity lower bounds, or the strongest monotone formula lower bounds are now known by essentially using a related method to this. And it's also been used for other lower bounds in proof complexity and communication complexity, often in relation to these two things. Like these things are not mutually exclusive by any means. Usually, because of the obvious close interrelation between proof complexity and circuit complexity with these problems, there's sort of lots of give and take between these two things. And and the extension complexity, absolutely, yeah. So yeah. Okay, so now we've actually kind of hopefully I've at least convinced you that we could prove this, right? By this sequence of reductions. It's just concatenating the 3 reductions on the previous slide, right? And for the real case, like real communication proofs, which is what we actually care about for proving lower bounds for cutting planes. So instead we have what's called a real communication protocol. And there, instead of Alice and Bob exchanging bits.
So you didn't say before, but you said one thing, maybe you could go back to the previous slide. The previous slide.
Oh.
So here, the upshot should be, we have monotone circuit lower bounds, therefore we can get the lower bound for some formula. This formula has to correspond, let's say we have
Exactly.
click lower bounds.
Yeah.
Where the formula will have to correspond to a click. Now the click function is already
split.
It's already split. It's already an interpolation.
Yeah.
So you want to get now to a random one.
Yeah. This isn't really like a clique. It isn't really like a correspondence between clique and clique, though, in this case, right? Because we're always reducing to this CSP function.
So you have to show that we have low bounds for this.
Yeah, exactly. Oh, I'm not done. Yeah, I'm not done. That's in a second. I was just sort of, yeah. We can also do the exact same thing for sort of real communication protocols. And now we have a real monotone circuit, which is, the gates are just monotone functions on 2 inputs, and they have to output 0 and 1. That's the only sort of constraint that we require. We have really good lower bounds on these things, so they're well understood. And the corresponding communication model here turns out to be able to simulate cutting planes. And maybe I'll talk about that a bit tomorrow. And so now we just concatenate the reductions in the previous slide. So Rubish and Pudlock sort of proved, apparently a while ago, this was announced in a paper on ECC back in December, that they can solve this problem, basically, relating the circuit size to the communication complexity size for real circuits and real communication protocols. So we use that result. And I'd also like to point out that in their independent proof of our lower bound, they don't do this 3-step process. They don't actually even use this. They have a completely different way, like sort of a simplified way of looking at it. So, okay. So just to remind you where we're going, we still want to get lower bounds for cutting planes. So this tells us, just like Avi just said, that now we actually have to get the circuit lower bounds, right? So what does this mean? Well, it means that if we start with a random f, we need to understand what these outputs actually look like, right? What does this CSP function actually look like?
Because you said usually you go the other circuit lower bound, so you go to communication complex.
Yeah, well, that's true for like formulas and stuff. Yeah, for formulas, the connection goes this way. But in this case, because we have such strong techniques for circuit lower bounds, like the method of approximations, it's really more convenient to go the other way. Yeah, so this is kind of the main thing that we need to do. We need to figure out what this looks like and try and prove a lower bound for it. So our way of engaging it is going to be sort of the standard method, one of the standard methods, I guess, for proving monotone circuit lower bounds, which is going to be the symmetric method of approximations. So this is a really nice general way of proving lower bounds against circuits, and it also works for real circuits. So we start with a partial monotone function. And now I'm going to there's going to be this kind of funny set, which is going to, in some sense, represent how scattered a set of inputs is going to be. So if I take I'm going to call A1 S of S, where S is a set of inputs, and S is just some real number, or some integer, sorry. So it's going to be the size of all the inputs in S. Well, there should be the cardinality of this set, sorry, such that if I take any conjunct of width S, I'm going to count how many strings it covers. So for any conjunct of S variables, not negated, just any conjunct of S variables, count how many strings in S are covered, or would output 1 on that conjunct, and then take the max over all possible S conjuncts. So in some sense, if this is small, this is a measure of, this would mean that no conjunct of S variables can cover lots of inputs in S. So it's like a measure of how scattered or like spread out this set S is. And it turns out for monotone circuits, this is in some sense exactly the parameter that we should be studying. So there's a very nice general theorem due to Yuchna, which says, any monotone circuit computing F has size just, this term right here, where, the lower bound is roughly the number of inputs, so the ones and the zeros, and you compare that to how scattered the inputs are. Okay, so here we're going to look at how many of the ones can be covered by a width S conjunct. And here we're going to measure how many of the zeros can be covered by a width S disjunct. And by covered there, I mean output 0 on it. So we would really like this to be small.
What is S here?
S is just, just a parameter, non-negative integer, between 0 and the number of input variables.
It's a low one for every S.
Yeah, this works for any S. Yeah, and in fact, it's more general. You can have multiple parameters here. Like, I can trade off the parameter here with the parameter here.
You can already think that it tells you that monotone circuits cannot do much better than writing the function as a DNF or a CNF.
Yeah.
And this parameter S is a trade-off between this number of errors.
Exactly. Yeah.
It's so pathetic. I mean that it's a simple thing. I mean how many things something implies, but that's a weakness of I guess of monotone circuits.
Yeah.
That's what Rasbow and Robert. I should point out it's the same method that Armin Haken calls method of
bottleneck counting.
The bottleneck counting, which he uses also in his monotone low bounds.
Mm-hmm. Yeah, it's identical. You're absolutely right. It's completely identical. It's also identical to this symmetric, like this lower bound by these Berg and Ulfberg for these monotone circuits, like this monotone circuit lower bounds without sunflowers. So it was this paper back in the 90s that they do exactly the same thing. Okay, so what does this tell us for us? Well, it means we need to understand kind of two things, right? First, we need to understand what the sets of ones and zeros really look like I said a second ago. And also we need to understand what this A1 and this A0 looks like for these particular sets of inputs for random F.
Let me ask you, so you're going to explain it today or tomorrow? It seems technical. So
yeah.
And given the time, I'm just wondering what you're...
Yeah, I have slides for it. I'm happy to fast forward and talk about it more tomorrow. But yeah.
Yeah, so time-wise,
yeah, time-wise, I guess I'll just clue up and I'll say, I'll explain it. I'll explain exactly how we do that sort of tomorrow.
What is it called symmetric?
It's symmetric, well, mostly due to the symmetry between these two things, but the method of approximation, it's just the symmetric method of approximations because in Rasborov's original method of approximations, you just approximate every gate with a DNF. And to prove this, we're going to approximate every gate with a DNF and a CNF. So it's like I'm going to approximate both the zeros and the ones. And I relate the two as I work my way up the circuit.
Is that not included with the symmetry of symmetric Boolean functions?
No, nothing like that.
No, it's really the clicks and colorings in in the monotone proof of click, they behave very differently. I mean, they are approximated differently, and so in the Haken lower bound proof, it just picks a function that's already self-dual. If the function is self-dual, you treat the DNF and the CNF in the same way. So, and I guess a random
one, it does actually turn out to be treated in almost an identical way. So maybe I'll just sort of skip over the description of how we do it, and I'll actually just say that more or less it boils down to the fact that random formulas are good expanders. Which is probably what you would expect if you've ever seen anything in this.
Which is the only reason
yeah.
These things, proof complexity, low bounds work.
Yeah, exactly. Yeah. So one thing I'd like to say is that just in terms of numerology, I guess, this k right here, this log n, it's too big. We'd love for it to be true for constant. But the reason we can't get constant here is because of sort of a problem with this method of approximations. It's this s to the s factor ends up killing us. We'd love for this to actually be like a 2 to the s factor. And then we could get it down to constant and potentially even improve this n over log n and the exponent to an n.
You think it's true for constant with high probability or just for some probability?
It's, OK, so this with high probability statement, it's really over whether or not this is unsatisfiable. The real problem is with this theorem. This just needs to be improved in general. Now, maybe we can say with high probability, we can apply a different theorem here, like somehow sharpen it using the fact that I know it's random. But yeah. OK, cool. So just to conclude, just to wrap up. So yeah, so we get the first exponential lower bounds and cutting planes proofs for random CNFs. And in fact, this is for any split formula. OK, so it's yet another application of this monotone CSP problem. And
what do you mean for whichever way you partition the variables? What do you mean any split formula?
By the split formula, I mean for I was calling back to the interpolation, where we think of the formula, like in the interpolation method, it only works in these formulas where the variables are partitioned in a very particular way. So this is the first one where we get anything that looks like, that doesn't look like that. I mean, yeah, the obvious question is really, I mean, what's nice and what is also frustrating is that this works so well for monotone circuits, and ultimately it boils down to sort of the same three tricks, like expansion and the fact that monotone circuits are incredibly weak, right? So we'd love to sort of develop some kind of framework to engage non-monotone circuits in this setting. And really the problem here is the relation between the search, this relation between the search problem and the CS and the Karchmer-Wigderson game dries up. That doesn't really work anymore. Because remember, if you look at the truth tables, on the ones, they're almost always red, and on the zeros, they're almost always green. So like, there's lots of places where they differ. They could output any one of those. I mean, another related problem for communication complexity, if you're interested, is whether or not we can prove a lifting theorem for size. So there's lots of lifting theorems that work for this, and maybe you can use some of the tools here. So we know that all these sort of objects work for size as well, so maybe there's a way to lift things over. And there's an obvious question is whether or not other lower bounds for cutting planes can be obtained by this. So I'd like to point out that Rubesch and Pudlock also prove lower bounds for this weak bit PHP. So it's a weak bit pigeonhole principle, which is like the regular pigeonhole principle turns out to have small cutting planes proofs. But if you kind of make it a bit more indirect, you can still get lower bounds. But I'd like to point out that kind of the thing that, in proof complexity, the thing we would love to see lower bounds for is Citon. And this technique is actually, it's not going to work. So the problem is that in this equivalence theorem where we show cutting planes and like between this RCC and these circuits, this RCC proof system is too powerful. It can just solve Citon in like linear size.
Citon is just random sparse linear equation.
Yeah, good. Oh, yeah. Sorry. Thanks. Yeah.
It's important that you have CNF formulas as opposed to.
Yeah, it should work for other things too.
But here, I mean, the reason why it breaks Citon is because they are linear.
Exactly. Yeah, more or less. Yeah.
But linear over F2, right?
Linear over F2, yeah. this turns out to not be a problem for the real communication. Like they can just handle this problem. Yeah. Yeah. I can show you the proof offline. It's quite simple. Yeah. And then so this suggests that we're still not done studying cutting planes. So we still need lower bound techniques. We've shown an equivalence between this RCC proof system, and this lets us engage cutting planes on new functions or on new tautologies, but we still don't have like a direct understanding of what's going on there. Okay. Anyways, yeah, thanks for having me. It's been great.